So here's the prompt. Now, what I want you to do is while we're thinking about a particular system here, right? How might an autonomous vehicle interact safely with pedestrians and other vehicles on the road, right? So let's imagine that we're trying to create something like an autonomous vehicle. And we're going to now go through this process of what our expectations are as human beings for an autonomous vehicle in the sense that it would then interact with the world in a way that is both safe for pedestrians and other vehicles on the road. Okay? That's what we're going to be ideating today. Does that make sense? Any questions before we move on? Does everybody know what I mean by an autonomous vehicle? I feel like probably everybody's seen one around here, probably. Last time I actually had people from Ford in the audience, so I think they got a lot of great ideas out of this workshop. But so anyways, what we're going to do is we're going to take 1 minute, and I want you to ideate everything that this autonomous vehicle would do in the world. Okay? And I'm going to give you 1 minute to ideate as much as you can. So one idea per Post-it note, and I want it to be completely silent in here while that happens, okay? Just assume what your expectations are about an autonomous vehicle doing something in the world that adheres to the how might we prompt, right? So like what fits within this framing about being a safe vehicle for pedestrians and other vehicles from the standpoint of what does it do in the world, right? I'm going to leave it as vague as that, okay? Cool. So you have 1 minute. Start it now. So one idea per Post-it note. And sorry, I hope we don't run out of Post-it notes. I'll see if we can get more if people run out. Okay, and here's our first random prompt that's going to change maybe the way you think about this. So what if it took care of the small things? How would that change what it does in the world? So I want you to think about that too. That is a great question, and I'm going to keep it as vague as that. What do you think is a small thing? That's the question. Okay, that's it. Is that pretty fast? Yeah, okay. All right, so here's what we want to do now. For the next couple minutes, I want everybody to basically announce their idea. Just say what's on the thing. I don't want you to explain it more than that. I just want you to say what's on there. If people really need clarification, that's fine to ask a clarifying question, but it should be super fast. And then you place it within the section of the map around the does, okay? But I want you to do that now as a group. And so just go around, say the ideas, put them on the board. Go ahead and do that. Okay? But you have to say it out loud to the rest of your group. So take 2 minutes to do that, maybe 3 minutes. So the next one we're going to do is we're going to do senses. So again, for this autonomous vehicle, what does the autonomous vehicle need to know about the world to meet our expectations in the way that it works? Okay? So I'm going to give you 1 minute to do that, and I'll throw in a randomized prompt at 30 seconds. So go ahead and get started. So I'm going to give you 1 minute to do the says section, and I'm going to throw in kind of the randomized prompt around 30 seconds as well. So why don't you go ahead and get started. So what does it need to say to help its human operators in some way? Yeah, also, you could think about displays. How does it communicate in general, its state, what it's doing, why it's doing it, anything like that. Okay, and then the randomized prompt is, what if it could talk with multiple people at the same time? Okay, so the next section to fill out is thinks, right? So what is the starting point of understanding? What are heuristics? What are rules, either written or unwritten, that need to be there? What makes this thing not stupid from the beginning, basically? How does it avoid simple mistakes? Okay, so 1 minute to ideate. Go ahead, get started. All right, so let's do feels. This is one where we're definitely pushing the analogy to the breaking point and probably going over the breaking point. But what I think is important here, right, is what are all the different things that we need to satisfy when it comes to the different aspects of this framing. And so one thing that I've found to be helpful here is that sometimes people can interpret a particular factor or outcome or optimization kind of like a dimension to be either good or bad. So I would just say whether you're trying to minimize or maximize this or whether it's good or bad, basically when you write these things down, okay? But I'm gonna keep it purposely vague, and there should be more than one thing though. And I'm gonna give you one for free. It probably shouldn't hit people, okay? So I just took that away from all of you. Now you have to come up with other ideas, okay? So I'm gonna give you 1 minute to do that, please. Okay, and here's one randomization prompt, is what if it took the gray areas into consideration? Okay, and that's time, but I want you to write one more Post-it note, and I want you to come up with an unethical idea. I'm sorry, what? Yeah, an unethical idea. Just one. Hopefully none of the other ones were unethical. All right. So now I'm going to give you, again, about 2 minutes to place these down on the map. So go ahead and do that. And maybe identify the one that was unethical, or leave it up to them to try to decide if it's unethical enough. All right, let's finish this up. The next thing that we would usually do here, sorry. So everybody, let's do this. Yeah, please feel free to sit down. I'm not going to make you do this right now. But I think the next thing usually what we would do is we'd look together at all of the different ideas that we had considered. And then we would basically vote them based on some type of prioritization, okay? So if you can hear my voice, clap once. If you can hear my voice, clap twice. All right. So basically voting is this idea of how do we take the output from this type of ideation to now move it on to the next stage of how are we considering to build things like prototypes, that type of stuff, right? So what we would usually do is something called voting, which is where there's a lot of people that sell these like little circular sticky notes. They probably make an awful lot of money. All you need to do is use a Sharpie, and then I would give you some number of votes. So in the number of things that are up on these boards, I would probably give you like 5 to 10 votes to vote across any of the different sections for the things that are maybe most important. And so one of the ways that we could consider what's most important here is what's industry differentiated. But it could also be what are like table stakes for us to get into the industry. It could be the things that we don't know the most about. It could be anything like that. So I think it's really important to think about, these prioritization methodologies. It really comes down to what are you trying to learn, right? So in this case, that would be the next thing. But I'd like to know, like maybe if a few people would be willing to share, what was the best idea or the most interesting or novel idea that people came up with at their groups? Any volunteers? Anything? I'm sure there's something. So gestures from the passenger, basically, or from the people out in the environment? The environment. Yeah, cool. That's great. What else? Yeah.
Something we talked about was personalization.
Okay.
So different people have preferences around safety.
Personalization for safety, way you drive, anything like that? Yeah. Really cool. Yeah.
Yeah, one thing we talked about is not about navigation part, but if you come back and you're tired and the car senses that makes you feel good.
Okay. Tries to make you feel better if you feel bad in some way. Okay. What else? Yeah.
Ability to hear, not just see. So let's say you're going across a train track that doesn't have a
Yep.
blockage, but you can see the train through this.
That's really great. Yeah.
A similar concept is if the light is turning red, you get a voice in addition to the sense of the light.
Yeah. Okay. Great.
For unethical, a lot of us have things related to not doing things that would harm, the passenger or other people, but someone had the idea of not harming other cars in some sort of competition for a higher rating vehicle.
Great. Awesome. No one came up with like a bar car? I feel like that always comes up every, okay. Well, once you don't have to drive. Anyways, so what was maybe the worst idea? And again, it doesn't have to be your idea. You don't have to say whose idea it was, but I want to know, like, what were some bad ideas? Yeah, bar car, maybe. What were some bad ideas? Driving through a parking lot to get, I mean, people do it. What else? Anything else? No? Okay. So, the whole point of this exercise is really that we have interrogated this system or this idea of what an autonomous vehicle would do within this framing from a lot of different angles, right? And there's overlap between all these angles. So it's not necessarily that each one of these sections is exclusive or not interrelated with the other sections, but we've been able to really explore this space amongst multiple people. And ideally you would have not just, like in your group, you would have people that were engineers, designers, compliance, legal, product people, data scientists. You'd want all these people providing ideas and the ability to look at a system kind of from all the way around. The next thing is that because of dot voting, you now have a set of things that you need to go and find out more about. So in the case of if there were a bunch of data points that you need to go off and collect, you need to see how would we actually do that? What type of sensors would we need to collect that data? What types of models would we have to build? When you look at something like the Thinks, what rules do we need to adhere to? Can we build models that adhere to those rules? Do we need to build ensembles of models? Or do we need to build truly deterministic kind of safety harnesses around these models to not allow them to do things, which is problematic in its own sense. So these are all things that you can now go off and start to do. And the next thing we're going to talk about after this break, I'm not going to make you do it, so don't worry, there's only one more exercise later today. But another thing that we can talk about is also worst cases, right? And so that was the reason why I asked the question about what was unethical, is we have to understand the space of not just what's good, but also what's bad. And so we'll talk about this exercise that we do that's referred to as confusion mapping, but I usually think of empathy mapping for the machine and confusion mapping as kind of being two exercises you do together during the ideation phase. So we're just at 3 o'clock right now, and so everybody has a half-hour break. So come back here at 3:30, and then we're going to continue on with a little bit of the ideate, and then we're going to move into prototype and test. And then that will complete the day at I believe, 5 o'clock. So thank you, everybody. See you in a little bit. Thank you for coming back. So what we're going to continue on here is we've been in the ideate phase. I'm going to just talk a little bit about one more workshop before we finish off with ideate, and then move on into prototyping and testing. And we're going to do one more exercise kind of in between now and then. So the last thing that I want to talk about for ideate is something that I refer to as confusion mapping. And so, this is related to maybe one of my favorite Alan Turing quotes ever, which is, if a machine is expected to be infallible, it cannot also be intelligent. And this was when he was talking to the Mathematical Society, I think in 1936 or something like that. And what he was really talking about was human beings. That when he was talking about other mathematicians, is that if something is like automated in some way, but it doesn't make mistakes, that probably means it's not trying new things, is what he really meant, right? And so from this perspective, when we talk about machine learning, and especially the whole purpose of, say, confusion mapping, is how can things go wrong, and then maybe how do we get ahead of them in some way. And so this is related to a confusion matrix, and this is an animated GIF that comes from the Google human-centered machine learning. And so I like this one. I mean, I think maybe the emotions are not exactly appropriate in all these cases, because true positive and true negative are actually good things, right? Like you want that because that's in some way what the ideal understanding of the world is. And if people are not familiar with this, so what we're saying here is that reference is kind of the truth of the world in the way that we understand it. So, and when we talk about prediction, it's like, what is the system trying to do or think should happen? And when we say positive, we mean that it, say, should take action. When we mean negative, we mean that it should not take action. Or you could also think about it in classification, that it says, yes, this is a thing in positive, or no, this is not a thing in negative. But what's really interesting is not so much the positive here, which we refer to as true positive, or the negative here, which is true negative. It's that the system thought it should do something and it did, or the system didn't think it should do something and it didn't. What we're interested in is actually the false negative and the false positive cases. And not always is false positive or false negative just bad. It can be bad in different ways. And the value across this landscape is not linear or equal all the time. And so, for example, if we were building some type of system that would predict whether a particular X-ray showed cancer in it, a false positive would mean that we did think that there was something there, but there actually wasn't. And that would mean that we could potentially then take action to remove something, maybe create some type of therapeutic action that could be more harmful for something that wasn't actually there. And a false negative in that case was that we didn't think something was there, but there actually was. And so there could be cancer, but we don't take action on it. Now, the opposite side of this is that, let's say we go back to the automotive example, right? In the case of an autonomous vehicle, say we're building a system that detects people in front of the car. A false positive would be that we thought there was someone in front of the car, but there actually wasn't, and so we maybe slammed on the brakes. A false negative would be that we didn't think that there was someone in the car, and someone in front of the car, and we just kept driving, and so we hit them. So there's clearly differences in what is false positive or false negative as far as like impact for not only us as users of the system, but other people that are impacted by the system itself. And so, when we talk about confusion mapping, and I'll show you how this is done in just a second, is that, for these types of non-deterministic systems, because it will not have a perfect understanding of everything about the world, because they're built based on looking at data to try to perceive certain types of generalizations or patterns, and doing it in a way that is not always fully understandable, and I'm going to talk about interpretability in just a minute, that we need to know what does it mean for them to fail. And accuracy is not enough, right? Just because you get something like 99% accuracy, there's still the 1% that is impacted in some way. And how are they impacted is incredibly important when we consider the ideas that we're creating. And when we talk about like actually discovering the potential worst case scenarios, this then starts us to think about how do we either, again, build ensembles of models, how do we build kind of cages around our models, how do we build systems that will try to avoid these worst case scenarios in some way, especially if they're incredibly impactful. And then I think it's really interesting because you start to understand what types of systems do you need to simulate to understand how these problems come about. And so the way that confusion mapping works is it's a mapping activity, so that usually means still the idea of private ideation. In particular, I have people imagine what would it mean for this system to have a false positive and what would it mean for the system to have a false negative. So in the case of an autonomous vehicle, what would it mean for a car to imagine that there was or was not something in front of the car? And what are the different types of impacts that could mean? Or what does it mean that if it does not correctly detect that there's a car that it's in the other lane? And so these are all situations that could come up that have different types of problems that come about and different impacts, actually. Customer outcomes, business impacts. And then you would rank these things based on severity. And that would then give you this like list of things that you need to go off and consider. And we're not even talking about frequency yet because we haven't built this system, right? We haven't actually built it or trained a model in some way with data. So we don't know how often these types of problems will come about. But at least we're going to be going into the building of the system or the consideration of prototyping the system in a way that would take this into mind. So I think it's a really important, interesting thing. So, a prompt might be like, how might an AV make mistakes while driving? And from that, you then have this like list of worst cases. I'm not going to go through this kind of workshop right now, but it's very similar in structure to the way we just did the last workshop. And it's about kind of from the entire group of people, how do engineers, designers, product people, compliance, legal, passengers, all kind of consider those worst case scenarios. So yeah, that's confusion mapping really quickly. The next thing we're going to cover is we're going to dive into prototyping, and I'm going to show you a particular technique for prototyping I think is pretty effective. So when we talk about prototyping, what are we really using prototypes for, right? Why are we building prototypes at all? Why are we not just building the actual system? And part of the reason why is that we need to be able to understand whether people can interpret what is going on with these systems when we build them so that they, when they're taking action or when they're utilizing the results of these systems, they're meaningful in some way and they're valuable in some way, right? The trifecta that usually we try to go to, which I think is from Marty Kagan, is really this idea of valuable, feasible, and usable, right? That's really what we're trying to get at, is what are those things for us with these systems? And so, this is a kind of classic trade-off discussion about interpretability versus accuracy when it comes to different types of models, especially when we talk about machine learning. But this is going to be the only AI machine learning joke that I'm going to use in this entire topic. But so a mom asks, why did you kick your sister? And the kid says, well, my attention was on her. Mom, be more specific. Because of the vector, huh? C embedding 122, 01, 13, 23, 199. So all this is meant to say is that there is kind of this expectation of explainability and interpretability, not because we need to know exactly what's going on. We can see what is exactly going on with a lot of these systems. We can actually trace through the process of how inference is happening. What we can't do is actually understand how it impacts the ability to use this information towards a human decision. And so I think there is this difference between explainability and interpretability, and I've seen people kind of say explainability is generally how to a practitioner does this system work versus interpretability, I think is more important because we're building these systems not for other practitioners, but for regular people. And so it's akin to the idea of A doctor goes to school for many, many years to understand something very basic about the human system. And when we, as patients, have to make decisions, we have none of that knowledge. And so they have to make their deep knowledge within the system interpretable to us to be able to make decisions that are in some ways life or death. So that's really important. I do want to point out this resource. This is a great kind of online book. It's freely available about interpretable machine learning. And I pull a few examples from here, but I think one of the things that's most interesting is actually Christoph points to this paper by Tim Miller in 2017 about using different type of psychological studies that have talked about what are explanations, and then assembles essentially this list that I think is a good starting point. Now, I'm not going to go through each one of these. What I think is interesting, though, is two very particular things that are almost at opposites with each other. So the idea that explanations should in some way be truthful, but also should be coherent with our prior beliefs. Now that seems really problematic to me, right? Especially when we talk about learning new things or learning new information. So I think it's something that's very interesting, and I will get into a little bit more about this, but I think explanations are really, really key when we talk about how systems are actually interpretable. And so one of the things that I think is most important when we talk about interpretability for these types of systems really comes down to this concept of counterfactual explanations. And so this is an example from Lime, which is about the idea of how do you make things like image analysis systems or NLP, NLU systems understandable about why it actually made a decision. And so in this case, there's a picture, which to me is a fairly confusing picture. And to a machine, it's incredibly confusing. So you can see here that it's a dog playing some type of guitar with human hands. And what's interesting about this technique is that it's starting to look at why in this image, if you had changed that part of the image, it would not have actually classified it the same way. So you can see here that part of it was actually triggering the electric guitar, which is because of the kind of the stem of the guitar. Acoustic guitar because of the orange color of the guitar, and then finally dog because there was a dog face, right? So what people really want is they want to be able to understand not necessarily the deep explanation of why this system works the way it does. Why did it classify in three different kind of ways, electric guitar, acoustic guitar, and Labrador? They want to understand why did that happen in some way that I can then take some action that is different than what is there today. And I think this is a paper that just came out about a month ago about how, and explainable AI is a new kind of buzzword in the industry, I think has come up over the last couple months. But what's fairly unique about this paper, and I'll link to it in my slides, is this idea of how do you actually look at how people ideally want to reason and make decisions, and that's the upper left-hand corner. And then how is it that explainable AI techniques provide the understanding of what is going on within these techniques? And then the bottom left is how do people actually reason with all of the biases and cognitive impairments that we have? And then what are ways that we can take a look at those biases and then create explanations that take those things into account? So I'm not going to go into this very much, but I think there's some really exciting research that is not only taking advantage of what is explainable from an artificial intelligence or machine learning system standpoint, but how are we now using these types of tools to augment the way that we are biased for or against understanding something. And so one of the things on the right-hand side, this is a medical diagnosis tool that they built for people, looking at a bunch of different things. And so one of the things that was fairly interesting about this particular case was that they were worried about recency bias information, that when you read from top to bottom, certain pieces of information may skew the way I then diagnose the patient because I saw that information first. And so they've rearranged the actual layout of this based on that cognitive impairment that we may have. So I think it's something that's really interesting and really important. But the way I'm going to get at it today is something that's maybe a little bit simpler, which is really around abstractions, right? And so abstractions are something that have been around for a very long time. When we talk about it from a, say, computer science standpoint, is how are you building different layers of abstractions so that you don't have to worry about the pieces underneath when you're, say, building a module on top of that. So here, it's the idea of like, we no longer have to write, we don't have to actually wire up circuit boards with transistors and resistors to build logic. We don't have to do that with assembly code anymore. We use high domain types of languages that are highly abstracted away from the actual physical hardware. And that's been beneficial because it allows us to use higher abstractions to build more interesting things. Now, very quickly as a story about abstraction, This is a New York Times article that came out a little while ago about the MTA in New York, which is the subway system, and why there has been, over time, and you can see here this graph is from 2012 to 2018, the delay in trains. And the reason why this happened was because of two particular policy decisions that interacted with each other in a way that people did not understand when they made that decision. So my question to you would be, what is the right level of abstraction when we talk about a subway system? And so this is one level of abstraction, right? The actual operator in the train tube driving the train, which is like a building tall car, basically. Is it something like this, a switch, which is a local kind of way to keep cars safe, trains safe, understand where they are on a particular line in a particular region? Or is it something like this, where you have a control center that understands the entire scope of the entire system to make these types of decisions? And what the New York Times found, and they actually created a very interesting visualization for this, was the two policies that interacted was having more spacing between trains to avoid accidents, and then to have more delays in the actual signaling system. And what was interesting about the way that the abstraction took place here is that if I just look at these two things, I would say, well, let's try to, give a little bit more spacing so we don't have as many accidents. And same thing with delays. We'll try to add some more delays. But we can see here on the left-hand side is that the space for impact and interaction or emergent behavior based on these two different rules is not an even space, right? The red means more delays. And so this level of abstraction would have been helpful to the MTA policymakers if they had had that. And so this is an example of where they have to make very complex decisions, and they have to do it with information that is incredibly important, but it needs to be displayed and interpretable to them in a way that makes sense to them to be able to make that decision. And I think whenever we talk about machine learning or AI or any of these types of systems, there's going to be incredibly complex logic that needs to be exposed in a way that people can make better decisions. So this is an example of that. So how do we balance these types of things, this complexity and usability, especially from a human-centered standpoint? And so, here's some things from, basically an article talking about abstractions. I think it was in an older computer magazine. But the idea of, reusability is interesting because there's a lot of different things that are out there today that people are starting to use to actually explain why a machine learning algorithm made the decision it did. And so one thing I want to use from the case study that we built. So this is an early prototype of a dispatcher interface for a particular job. So on the left-hand side, you have a bunch of information that is about the job itself. So there's a summary of the issue in a few words, some date stuff. There's a percentage score I'll talk about in a second, and then there's who was reported by, who's assigned, what are the parts that are needed. And then on the right-hand side is kind of this ongoing flow of conversation where there's actually a conversational agent along with multiple parties kind of discussing how to fix the issue. Now, the percentage was the thing that we were trying to test in this prototype. And what we were trying to test is the likelihood that this job, if assigned today, would not create a return trip the next day. Because that was incredibly important to the actual statistics or to the model, the monetary model for this work. So 94% for this job meant that the likelihood of it being good, it would not require this, was fairly high, right? Now the problem is if we showed someone 94% or 85%, they had no idea what the difference was between those two confidence levels. And it didn't make any sense to them. Right? So what we ended up doing from an abstraction standpoint is rather than just exposing something like the confidence scoring that's coming out of the model, we actually went to a system that was more like there are thresholds that we want to surpass based on some prediction system. And that moves us down the path towards actually assigning the job. And when we display that to people, we're not even showing them that information. It was not helpful as an abstraction for them to then make a better decision about what to do next. And so that's an example of where when we talk about why we're building prototypes, how we're building prototypes, it's to understand the output of these individual models, not just the actual classification, but also confidence scores, uncertainty, risk, right? These are all things that we need to understand when we talk about these types of systems. And I think we're starting to see patterns, right? Like this is an example of a SHAP model kind of explanation for what values have gone into this particular prediction. Now, it won't always be something that people can build further expertise on, which I think is important for abstractions. But there's starting to be more and more of these like UI modules that are out there. And I link to them in the slides if you're interested in checking them out. And there's actually a speaker later, I think it's tomorrow, Thursday, where he's going to be talking about this idea of explainable AI. And I think there's a lot of interesting models that are coming out of this. I don't think we're anywhere near kind of the sophistication that we are with, say, web usability or things like mobile usability, but we're still fairly early in all of this. So there's work to be done here, but there's at least things that are starting to work. And so I want to talk about UX patterns, right? So when we're building a prototype, there's a lot of different ways that, the quote unquote AI could be involved in the system. And so the first one is really assistive, right? A lot of the things we do with, say, spell checking, fraud detection, like these are all things that are kind of more assistive to human beings than they are just like doing the job. So being able to help correct errors tends to be the first thing that people focus on, things like that.